So just okay. Yeah. So some just what are we trying to do?
Yeah.
So first, what is an LLM? So you have kind of translation first
Right.
from a token to an embedding.
Yeah.
This is an LM head that does that.
Yeah.
This is just something that transforms like kind of you have a total of like 150,000 tokens that you can choose from, and it transforms that into different combinations of embedding. Here, let's say it's 1,024. So it's just like a big matrix that makes sense.
Yeah.
Then you go through layers. Here we're working with Quen.
Yeah.
So we have 28 layers. And each layer has a few parts. So each layer has first attention part. This is multi-attention. Then there is an MLT. And then there is some kind of normalization. Okay. There's a bit more. It's simpler. And so what we're going to do is we're going to extract the data after the normalization, after each layer, from layer 5 to 25.
So what is a layer?
A layer is attention plus MLP plus normalization.
Right.
It's kind of made up, one layer is made up of multiple layers, but that's a layer for the sake of our discussion. So we're taking this layer 5 to 25, and we're gonna push those into earlier layers. So the result of that, so let's say at the end of layer 5, you have an intermediate result, right? We're gonna take that and give it 5 tokens earlier to like layer number 0, and we're gonna add it as a bias. This is just a different way of just like changing the values, and so we're adding this. We're injecting it between the no, that's not. But we're basically injecting it before the normalization. And this is just to keep some level of same normalization so that it doesn't like become a big mess inside the model. And the other thing is we're compressing this thing. So we're not just like giving it, oh, this is layer number 5 and we're adding that on, because that would be not very useful. So here we compress it. Here we're doing what we call a downward project and upward project. Just imagine it like there's one layer that is 1,025. That goes down to 128. So it's a fully densely connected layer. It just goes down. And then you go back up from this 128 to 124. So it's just a form of compression. And this is to give it some level of bottleneck. Just like the tokens right now are a bottleneck with, so as we said, let's say 16 floats. Like this would 16 not floats, but it's the equivalent of one float basically. And with this, we would have 128x the amount of bandwidth that we give the model. And this is for each layer. So here we would have 128 times 20 the bandwidth. Just to give you a matter of scale of how much bandwidth we added to the model when it's talking to itself. And so, yeah, we're adding this residual stream. And basically, also for you, what's maybe interesting here is it's not that many parameters. So this is a small Quen model. This is, I believe, about 1 million parameters, which is like this is 600 million.
It's then maybe it's a bit more. I don't remember.
Like it's less than 1% of the parameters. It's comparable to a small LoRa in terms of like amount of parameters. So this is the first thing I did, and what you can see is the loss goes down.
Right.
Right. And so here I'm just training it on
What does loss represent?
the cross entropy loss. So basically, what this is what you train every model with, basically.
Yeah.
And what this is just how accurately did it predict the next token.
Oh, I see. So it made it more accurate.
Yeah. And so here I didn't do a full kind of like X to X comparison, but generally like being like for a 0.6 billion parameter model, getting in the 0.8, 0.9 range is quite good. And so here this is the training loss, and you also want to look at the, here I'm just gonna find the correct one. So this is a friend who saw that I had released my on my GitHub yesterday and just made a joke, and I got very scared. But I think it's one of these. Let's just check which one.
What is 1B?
That's like TensorBoard nicer. Let's just check which one. Yeah, I think this one. And so here you can see like the train loss goes down, but it's not only the train loss; it's also the eval loss, which goes down. Yeah, here the eval loss goes from 1.1 to 1.06. Like you have some level of like overfitting, right? But still, like it's
How do you measure it?
it's kind of like how much is the eval loss higher than the train loss. So yeah. Another thing which so now maybe does that make sense? First of all,
I think a lot of this is very new to me, so it's still like patchy, but I think broadly, okay.
What would help you?
I think it's a lot of the like terminology is just like a lot of new concepts, and then also having a mental model of like
what are the words that you don't understand?
So if we go
to one thing I should be worried about. You can do that kind of like
To this,
yeah,
to
go
this.
to it and then go further up.
or like,
So where does
am I
yeah, so like
than everyone else? You know?
so
Slightly social.
maybe just actually going again. Like what, so the original goal, and then like summarising the process you went through, and then whether you achieved your goal or not.
Yeah.
And what
So-
would an example?
So what is happening? The first thing is when you predict a token, you can only see the previous token. Like you just look at the previous token. Exactly. You can, but you can just see the text. And this is limiting because this one piece of text, when it goes through the LM head, it turns from about one float of information, about 16, like one brain float of information.
Interesting, because it's that maybe it's
Exactly.
matrix, and you're taking it down to
Exactly. So there's a very strong compression and decompression at the beginning and end of the
I'm sure
model.
there's something even
which goes from basically one brain float, one BF16. It goes from 17 floats up to the amount of like dimensions here 1028 times a brain float. So basically there's a 1000x compression and decompression at the beginning and at the end of the model. Beginning and end being before layer 0 and after layer 28. And what I'm trying to do is to give the model more than just one brain float of data that it can share with itself.
Okay.
Because through all of these layers, it computed a lot of knowledge. But then it has to lose most of it because we're going through that 1000x, and for a bigger model, it's more like 10,000x compression. And so what I'm trying to do is to let the model listen to itself in pieces, so that it can talk to itself not only with the single word, but also with more information from.
So you're giving the model you're giving the model all of the alternative words that it could have said, or are you giving the model the matrix representation of that word?
Yeah, I'm giving it the. It's not even the matrix representation of that word, because that would be just at the last layer.
Right.
At the last layer, you would kind of see like all the other words that could have happened. But there you still have to think like, if it wasn't the word glass, it could have been air, it could have been it, and it could have been frog. And if you let the model just predict with, hey, the last word was 12% glass, 7% frog, and 2% air, it's just like, what the fuck are you on about? Like, what do you want to tell me? What is the next word? I don't know. Like, it's 12% frog. Like, what are you on? I've never seen this in the past.
Right.
So it gets very confused if you do that.
Gotcha.
So what I'm trying to do is to integrate that a bit more deeply into the model.
So can you give me like an intuitive understanding of like what it is? What is this uncompressed? So the word is the compressed version.
Yes.
What is the uncompressed version? Like what is that? Is that multiple
It's
words?
an embedding.
It's like a conceptual.
It is a 1,000 dimensional array.
Yeah.
That represents that word. And
Okay.
that doesn't only
Does
represent.
it uniquely represent that word?
No.
Okay.
It represents everything. It represents every possible word and every possible meaning.
Yes.
So it's just, this is what the model thinks in. The model thinks in this 1,000 dimensional array language. And in this 1,000 dimensional array language, and this depends on the model, right? Some models think in 10,000 dimensional arrays. In this 1,000 dimensional array, the combination of activations of, for example, if 750 is plus 0.5 and 260 is minus 0.2,
Yeah.
this means fish.
So that embedding is like it's the meaning, it's the underlying meaning, and it resolves down to a word in this particular context. But presumably it can resolve down to a different word within a different context.
To some extent, yes. So that depends a bit on if I understood what you said correctly.
Yeah. So I'm saying that like one embedding cannot be like multiple words, or is it always the same?
Right. So what's gonna happen?
It's like
what's gonna happen is this embedding will get transformed.
Yeah.
The embedding directly has a direct like kind of transmission to like, okay, it's 12% this word, 2% this word, because that's what you do when you push it through the LM head.
Yes, it's like
you get the logic.
Ginginess versus glassness, or like
but what you do through the layers is you evolve the word from basically the last word was glass, the next word is water, or I don't know. The last word was water, the next word is bottle. So you need to go from you need to somehow form the word bottle, right? Through the different layers, through the 28 layers, you need to go from I don't know what the next word is to the next word is bottle. And so you're going to do this by kind of, first of all, like kind of asking all the previous tokens things about the past. This is the query. And you're going to multiply that with a key. And that's how you get the attention score. You're going to get a value. That's the Q, the K, and the V.
Right.
I
know that equation, but yes.
That's just a very, like, that's attention, basically.
Same word to the model.
Right. So, shall we go?
Yeah.
Okay.
Yeah, the word will evolve and you will derive meaning into it.
And so why does like passing the layers back into the other layers generate this result?
Yeah. So right now we don't pass layers back.
Right.
And so what happens is maybe over the 200 layer, over the 28 layers, we deduced that the next word was a water bottle, specifically that it was a full water bottle filled with cold, sparkling water. Gonna just make that as a thing.
Yeah.
You could deduce that from concept, from context of the rest of like, oh, it's outside and it's, I don't know. You can deduce that from the context. But when you just choose the word bottle, you get the average meaning of bottle.
Yeah, I mean, what you could
And
do
bottle
is
could be a glass
create
bottle,
a game for them.
could be a plastic
And
bottle,
then
could
if you
have sparkling
create
water,
credit
could have cold
drawings,
water, could have hot water.
that's as if it
You just cannot describe that it's a hot water bottle in one single word because human language doesn't work that
if
way.
you want, like, just set that as a given name.
And what happens is that when you kind of choose the word, you do something called a log problem.
Do you really think they
And basically you're
all of Scotland's games?
create a single, you're going to create a list of probabilities.
Okay.
And then you're going to pick just
we
one.
could do again.
So you lose the information that like, it could have been also a water kettle
You know, find the best.
at the 2% chance.
Yeah.
And you're going to lose the information that the water bottle that it chose was specifically a plastic water bottle with sparkling water inside.
Yeah.
And so the idea is just to be able to share that information, which you cannot share just with human language, to be able to share that with a bias or by sharing information with yourself.
Yes. Okay, so I think we're making sense so far. My next question is, why then do you compress? If you're losing so much information, why do you compress it?
Because that's at the end what humans will consume. Humans consume text. They don't consume Neuralese. And so you need to have a text output for you to be able to say, was it a good text or a bad text?
Right. Interesting.
And also, we're producing text because that's what we trained on. We trained on text. So.
But you said, I see, and it's, so the reason why it's you're compressing and then decompressing, that's the output, is that little bit, right? Is that like
the reason why I'm doing some level of compression is just because you don't want to overwhelm the model with very noisy stuff. And so some level of compression allows you to have more information density inside of it. That's it.
Okay. And so, does that mean you get a better? So you basically got a better model for a given size, a given set of training data. Now that it can speak to itself in Neuralese, is it now speaking to itself in Neuralese, or it's just trained in Neuralese?
How are you?
Yeah. So
do you
here
want-
comes the training and the speaking to
I have
itself.
a question around offering supplements.
I'm not sure.
So
So the goal is
essentially,
to get to a better model with the same size. Correct.
Another sort of settlement offer, and I'm wondering if there's any.
I think there's also just going to
requirement
be
send that through ACAS.
things that
Or
happen
can I
that
send it
are
directly to the claimant?
that we didn't expect. So right now, important concepts are saved in 20 different ways. So if, for example, the concept of a bottle, of a container of a bottle, is probably saved in 20 different places because it's an important concept. Whereas the concept of
you can have multiple
right,
embeddings.
so actually, you will have it saved in multiple NLPs across multiple layers. So you have like in the 600 million parameters, you'll have multiple. You will have more parameters that know what love is than that know what benzoyl rings are. Just because it has read
Can I
more
just
text
double
about
check? Like,
love
if I send
than
a
about
supplement
benzoyl
offer
rings,
directly,
right? Even though benzoyl rings are great.
can we then come to ACAS to get help with the code through?
And so, if you get to, my assumption here is if you get to pass the embedding to itself at a previous layer, it's going to make some of these concepts more robust. Because like you have already deduced love, and so you don't need to rededuce it every time from scratch.
So would you say it
But
makes
you can deduce it out of this Neuralese, and you can have less redundancy. So instead of saving love 100 times, you can save it maybe 25 times. And if you can save it 25 times, then all of a sudden you've freed up a lot of space for other learning.
Yeah.
And so this is one of the things that
either
I
way
think
you're
will
saying
happen. The second thing is for memory. I think this will be very useful. I think this will also increase the amount of computation that you can do with a single token. I think for reasoning, this will have interesting consequences. Like
and be clear, like
I do not know yet.
I
I just know we're obviously fucking
is that still okay?
numbing the model down and forcing it like almost like to do math with emojis.
If we added the other
And what if we stopped forcing the model to do math with emojis and allowed it to use mathematical equations? But it will be smarter. And it's kind of like, I do not exactly know what all the unknown consequences of this will be. I just know like, it feels very reductive how we're compressing 1,000 x. And on top of that, adding noise there. This is the temperature.
Got it.
Right?
Okay.
With temperature, also maybe sometimes don't choose the best word. So you're doing 1,000 x compression, and on top of it, not choosing the best word.
Or for the code through.
And so, what if instead of this 1,000 x noisy compression, you have
so I'll make sure that
something that has more bandwidth, less noise? I assume the model would
mention this
do
to
better.
the claimant yet, just because.
Okay. And so next question is, like why is this novel? Is this like a
Is that okay?
Yeah, I think it's still somewhat novel. It's not like you've listened to the Dwarkesh podcast as well. Like, they do talk about it as well. It's not like, I'm the first person who came up with it. The thing that I got surprised by is how little people actually do. What I mean by that is just like the amount of people who actually train models. Not that big. There's
how
not.
many people like
Okay, got it.
Yeah.
Just to check on
Yeah,
that,
I think that's about the right range,
might be a
right?
dumb question, but
And
there's
so
only one
thousands,
that
tens
does
of
that,
thousands.
response, right?
And how many of those train just like the model that everyone else is training versus something new? And so you don't have that many people who, like, I don't think every idea has been explored yet. That's one thing.
So like, could you could this be like? Could you then release this, and it would be like a better model for lots of different use cases?
It's
Is it a frontier model, or is it?
Yeah. So it has potential to be frontier. The reality of it is today training a model is very expensive. Today you go through trillions of tokens, you go on thousands of H100s. It's not something that is very much a hobbyist thing, but like to get the best models, you invest millions in them, right? And so it's less of oh, this is going to be the new frontier, and this is the new frontier now. I think that's not likely.
Sorry, so how about
but
the ETC?
It's more likely
Is
to
that
happen with like
written by lawyers?
just like distillation became very popular, and now even DeepSeek is doing distillation on O3. This will become a very common technique that people use. And the interesting thing is when you are the inventor of one of these very common techniques, you have some level of like just grandfather powering the market. And where this becomes interesting is this Neuralese.
Okay.
Right now, it's only compatible with yourself. Right? You can only talk to yourself in Neuralese because my Neuralese is not going to be the same as your Neuralese. Right? Because I might have 1,024 dimensions, you might have 2,000 dimensions. Already there's a mismatch. Or even if you have the same 1,028 dimensions, maybe you don't place the word grass at 750 is 0.5 and minus 0.2 in
Like
position.
how do you translate all of
Exactly.
versions?
So you need to translate my Neuralese to your Neuralese and vice versa. And if you need to do that, actually the most efficient way is not to train a translator from me to you, but to say, I'm gonna translate into a common language, which is just defined as like, this is the standard, this is English, English for models, Neuralese English, and Neuralese English just has determined that like grass is usually there, love is usually there, like how different concepts are just encoded in the space. And so then your Neuralese only needs to be translated into the common Neuralese, because then any other model can read common Neuralese. And like this, you only need to train one adapter per model. And this is going to be an open source company that kind of says, hey, look, you can train your own Neuralese adapter. Please do it. I'm very happy for every company to just use this free of charge. But average Joe who just trained his model or fine-tuned it or whatever doesn't know how to do that. It's also not his core competency. Like, even if you're actually a Claude or an OpenAI, you're like, I care mostly about my model being smart with itself, and it being working with other models as like kind of an afterthought, right?
That's interesting. So it's your play here. You want to be the person who will translate everybody's.
I just say, hey, look, this is the common language. I maintain the common language.
That would be great. Just
You are the common language, like standard.
Yeah,
Exactly.
Yeah.
And you get to train yourself to be compatible with this common language or not. But I think the market is going to demand it at some point, especially with agents.
Interesting.
And
So, okay, yeah. So see the.
Yeah.
That would be
It's
great.
difficult for me to audit whether that's like a reasonable supposition or not. But yeah, it's a nice idea.
and maybe I'm completely wrong, right? But
Appreciate that.
yeah.
Thanks very much.
Thank you.
And so I might be completely wrong, just like the guy who created Coinbase might be completely wrong on Bitcoin being a thing. But if it's right, I'm very right.
Yeah.
And
So how much effort does it take to become the common Neuralese for? You just state like this is a standard set of embeddings for.
But you need to be the best, right?
What does it mean to be the best?
There will be competing standards. Like, I'm sure Claude will be there and be like, hey, look, this is our version of Neuralese. Everyone adopt our version of Neuralese. Thing is, OpenAI, Google, these other companies are going to be like, yeah, not a big fan of adopting your Neuralese, right? Because then this puts me a bit under your thumb a little bit, right? You can change the Neuralese to somehow an architecture that is not good for me. But if the Neuralese is not controlled by my competitor, and we all agree that Neuralese conversations are going to happen in the future, great, it's an open source thing. And there, it's more like there's going to be probably at some point a few open source projects that try to do this, and you need to be the one that has the most traction, the most usage, the most is the easiest to develop on, is the easiest to adopt, that kind of stuff.
Yeah. So what does it mean for a set of embeddings to be better than another
Yeah.
set of embeddings?
So it needs to be expressive. It needs to be able to express very complex thing in a concise way. It needs to be able to be easy to train a model to it, so not finicky.
Yeah.
Like you can shape your embedding space for it to be weird for other models, then you will need more training to adapt to it. It's also like ease of use, like just like there's examples of hey look, here's a training script, here are some testing examples that can make sure that your translation has been done correctly. There's a lot of stuff to be done.
Nice. Very cool. Can we have a look at the codes? Like,
Yes.
also, so how does it actually like?
Yeah.
Is this like a standard thing? You take it and customized, or did you build it all custom?
So the way how I've done it is I've tried to make it easy to adopt, right? And so how do you make it easy to adopt? You use somewhat standard things. So the way how this works is with hooks. What is a hook? You know what a hook is? Okay. Basically, you can just like detect when something happens and kind of add some extra code there.
Right. Okay.
And so here we're taking a Quen model, a small Quen model, just this is playthings for me to be able to learn with it. This would be, for example, the standard embedding size here. So would it be 128? Would it be 256? Would it be 512? I don't know yet. This is like something that needs to be determined, right?
You said that embeddings in general are much larger.
Yeah. So, for example, on the Llama 70B, which I'd say is kind of like what most people actually run in production, that kind of stuff, that's 8,000 dimensions. So you're not giving it 8,000 dimensions of noise, but you still have a lot more, right? Here it would be, I'm simplifying, but 128 times more or 512 times more bandwidth. Yeah. So it's still significantly more. So it's pretty lightweight. So what do we see here, right? We have the Neuralese adapter. Let's see. So maybe this is the base thing. So we can start with this. This is PyTorch, by the way. Yeah. So here we also use Hugging Face. And we kind of initialize the model with all the things that it has inside, all the layers from pre-trained. And we use the tokenizer from pre-trained. So this is the LM head part. And that's it. And then we kind of define this adapter. This adapter is the thing that we've done up here. And so here before you remember I told you like we just take layer 5 and push that into layer 0. That's a little silly because it's hard coded. I just decided 5 layers. And so what would make more sense is to actually stack all the, I'm not exactly sure actually, is this one with stacking? So I have a few versions of this as well. So I'm just wondering which one I'm showing you and which one it is. But so the upward project and downward project, this you can just imagine as a big linear layer that goes into a small linear layer, and then a small linear layer that goes into a big linear layer. That's for you how to think about this. And these I just initialize with some weights that are not too big. This is because the norm goes up during the. You don't want eyes to be too big, basically.
And what is the bias in there meaning like?
So usually you have a node, and it kind of like gets input from all of the other nodes, and that's a multiplication, right? It gets a multiplication from like this times this is a plus or a minus here.
Yeah, yeah.
And then this neuron at the end has a bias, which is a constant that you add or subtract from it. And like this, the neuron fires or doesn't, or it just changes the activation behind it. Because afterwards, once you have this, you're going to push this through, I think, a serial function in this case.
Or do you have a printer here as well?
Hmm.
Do you have a printer?
I am not sure. It would be back there, but I don't think so. You can ask as well. Maybe Leander knows. Leander might know, but yeah. So yeah. But yeah, small, big. That's the.
And does the small big, does that like replicate what's happening when you chat with it?
The thing of yours
That's like
is basically down the
presumably
street as a bit of post.
This is just to give it that dimension. Right?
Yeah,
Like, this is I'm going from whatever the size of your brain is down to the size that I defined, and then back from the size that I defined back into the size of your brain. It's this part. Right. So what I did here, instead of just hard coding it, is I did attention. And I noticed that I'm using multi-head attention, which is silly because I'm number head 1. So this is actually self-attention. But yeah, this is just a bit silly. I just noticed. AI, thank you. But basically here we're attending to the 28 layers. And we're going to determine which of the layers has information that we want to keep. So that's it. So we're gonna pick some of layer 0, some of layer 8, some of layer 12, I don't know. And what's interesting there is actually based on the size of this latent dimension, it's gonna pick more or less from different layers. So with a smaller one, with 128, it will pull more from the later layers. But if you have a larger 512, for example, dimensions, it's going to pull from every layer kind of the same way.
Right. What's the intuition there?
The intuition is with 512, it has enough space to encode all the things that it wants, so it can encode from every layer. And with 128, it might not have all the space that it needs,
right.
And therefore it focuses on the last parts. And this is an intuition, but honestly, this is just code from yesterday, and so it might also just be I made a mistake somewhere.
Okay.
Like, yeah. But so basically, here we're stacking all the layers, so we're kind of extracting at every layer with this hook that we did. We extract after the normalization the values. We extract them, we stack them, so they kind of become this 1 times 28 times 2024. And then on this, we're going to perform attention. So we're going to perform attention on these 28 layers and turn it into a one. That is wrong. And this is just AI written, but yeah. Basically, it's going to look at the 1 times 28, the 1 times 2024. And then this will get compressed with the down project layer. The down project being the thing that turns the 124 into 128. And yeah, we're gonna make that smaller, and then we're gonna pass that along, and then we're gonna have a different MLP for each layer, a different up project here. Here I didn't even make it an MLP to start. MLP is just multiple layers, and up project or down project is just a single linear layer. And here I just did a one linear layer that kind of is different for each layer, so that it can add a different bias to each layer based on what it wants. So that is, in short, what you can see here. Okay. So here is where I set up the hooks as well. So here, for example, yeah, you can add the different hooks. So this is a forward hook on the end of the layer. And here it makes the snapshot. So this is the place where it collects the values. And then, so because actually we're doing two passes, we can get into this if you want, but it's just we need to create the latents. So we need to first do just a single pass that we're not going to look at the result, but we need to do that to extract what the intermediate thoughts, basically. And so we're getting the intermediate thoughts, and then we're injecting the result of our calculation. And this is the injection hook that we do before the normalization. Here is the definition of the snapshot, where we're kind of like taking the output here. And there is the injection hook, where we add that. And here we kind of adjust the output with output plus bias. And we also collect some information about what does the bias look like, what was the norm looking like before, what does our adjusted norm look like before, and how strongly did we adjust it. This is useful for us to just like know how much did we fiddle with it, how big is the bias. Yeah. This is useful to know, like, oh, is it just not using the bias? Is it using it super strongly and it's overpowering everything else in the model? And these were some of the diagrams that we saw with the adjustment ratio, the bias norm, the compressed norms, these kinds of things.
Yeah.
So just help me to kind of understand what's happening inside.
What does the actual output of this look like? Is it like a big array or something?
I mean, the end output is text as well, or the end output is predictions of text.
Yeah, but what is the model itself?
The model itself.
Like, what is the final thing returned?
At the very end, you get an output, and this output is 1 times 2024. And then this gets pushed through the LM head, which is this tokenizer. And this kind of creates probabilities. And then you perform a soft max to it. I mean, that's not quite true. Like, you do a log probe and a soft max, but basically, this allows you to turn this embedding into a text token. Nice. Okay.
I mean, I definitely didn't get all of that. Probably some 50%. I'm much better conceptual understanding than I did before.
Cool.
Yeah, I think this is like probably several steps ahead of where I am in terms of like understanding the models. But still very worthwhile. I think. Yes, it sounds like you've like simplified down. So like even from your goal of like doing all these things to like some intermediary set of processes you're going through here.
Mm-hmm.
So what's next for the project?
Do you want to know the technical side or the human side?
Let's go to the human side. I think I'll have
The human side.
limit where I can get to on the technical stuff.
The human side is, I think, getting proper compute to train it on would be very useful.
Mm.
So if you know anyone who has like cloud credits because they want them at the hackathon,
Have you tried? You must have already tried SF Compute to look at that. And
honestly, it didn't look too hard.
Right.
Um,
It's like very cheap.
Yeah. I mean, ideally, I'd get it for free,
Yes.
just for the psychological reasoning of like I don't hate to work.
Yeah.
Because that feels weird.
Yeah. I mean, have you already got a load of credits? Like, because you can just start an AI startup and then just get credits from people.
I mean, I just didn't do it yet.
Yes.
Um,
You should. You can. I have a friend who knows somebody at Google who get credits.
I'd be happy to talk.
Yes, I will message.
So that's one piece. And the other piece is, I think, right now I'm doing this and I'm understanding what I'm doing. But discussing this with people who actually know their shit is useful. And so I've spoken with some people, and it makes sense to them, but like what I'd like to build for myself is some sort of community of people who do understand this and who maybe also do their own research. And where once per week we kind of talk through, hey, look, what did you build? What did you implement? Why weren't you faster? Why did you go that way? Why?
Yeah.
That's things that we do in the house, but that the people in the house don't train models and create custom books for them.
Yeah.
And so like they can understand it on like you, like, oh cool, this is how it can work.
Yeah.
But they cannot push back and be like, oh, why did you use a hook and not a callback or whatever?
Yes. There must be a community of people there in London who do this.
Yeah. If you know them.
Yeah. But it will be like